Okay.
All right, good afternoon. Welcome to the seminar. So it is my pleasure today to introduce Dr. Marco Colomba. He comes all the way from University of Leeds, UK. And well, he's originally from Italy, but it was way before the whole story. He's going to tell you everything. But a quick biography. So he's a senior research fellow at the University of Leeds in the United Kingdom, where he moved in 2013 after obtaining his PhD from Politecnico di Milano in Italy. And he currently holds a research fellowship from the EPSRC, so this is like an SF kind of
Yes.
in England, entitled Towards Comprehensive Multi-Phase Flow Modeling for Nuclear Reactor Thermohydraulics, and has been involved in multiple EPSRC-funded projects on different aspects of nuclear thermohydraulics. And his main expertise is in the modeling and computational fluid dynamics of multi-phase gas, liquid and boiling flows, natural recirculation, and passive cooling. And actually, I'm hosting him for the next week of class as part of his fellowship here at NC State, and maybe you will come back also in a year or so, right? That's
yep.
the plan.
That's the plan.
Yeah. Please welcome Marco.
Thank you very much. Thank you for having me here. So I said I've not been in Italy since a few months, so that's fine for that. So in this talk, I would like to summarize the research work that I've done in recent year at the University of Leeds in different areas of fluid flow, in particular of multi-phase flows that are relevant for nuclear reactor thermal hydraulics. So what we have to deal with is fluid flow problems. Now, it doesn't matter if we are in a reactor or in any other industrial or engineering scenario or in any natural process. We can describe those flows with balance equation, right? So we can have a mass conservation equation now, single or multi-phase. In this case is single, but we will move soon to multi-phase flows. A momentum conservation equation, then we can add, depending on the problem, an energy conservation equation if we need the thermal field, turbulence model if it's necessary, species conservation if there are some chemical reaction. And if we have those equations and the proper boundary condition, the proper geometry specified, in theory we can solve any fluid flow problem, but the issue is those are quite complex partial differential equation, and except for very simple condition, a solution of those equations is not available yet. And that's why we use many times and more now computational fluid dynamics, that if we have to describe it in very few words, very simple, is essentially a series of computer-based modeling techniques for the numerical solution of fluid flow problems. And looking at all the software that there is available now, more or less they have the same structure, and they go through the same steps. So at the beginning you set up a geometry and you build a computational grid on that geometry, as in this case here. Then the governing equations are discretized on that grid, so you pass from a system of partial differential equation to algebraic equation that can be solved. That means the solution will be it will be discrete, so it will be available only on specific points, and of course that immediately translates in the fact that the more computational grid you have, the more resolution you can have on your problem. Then you go through the solution of this system of now algebraic equation that can be done with numerical technique, applying the boundary condition proper to your problem. And then when you have your results, you can do the nice post-processing that end up in nice pictures like this one. So that's very, very briefly to start on CFD. So what I do is mainly, my work is mainly focused on trying to apply CFD in different area of nuclear reactor thermal hydraulics or related to nuclear reactor thermal hydraulics, and use computational modeling to improve the capabilities we have to predict this condition, and in particular are focused on two areas. One is boiling and the prediction of boiling heat transfer, and most importantly the critical heat flux, and try to do that with models that are as physically based as possible. Now, that was the original plan. Because starting doing that, I realized that then I spent most of my time trying to predict bubbly flows, which are only a portion of, let's say, the boiling problem, and how the bubble distributes in a flow, and how also the bubble population evolves. And the other areas is convection, and develop some CFD model that we can use to model passive cooling in particular with confidence, and being able to estimate the passive cooling and effectiveness. And in particular, I've focused on the external reactor vessel cooling strategies. These have been done in a series of projects supported by the EPSRC, which is the Engineering, Physical and Science Research Council in the United Kingdom. So let's start with boiling. As you know, that's a very efficient, one of the most efficient heat transfer processes, and for this reason is widely used in nuclear reactors. We have, boiling water reactors, but some degree of boiling always happen also in pressurized water reactor, and boiling is a fundamental part of many accident scenarios. It is very efficient, but at the same time is really, really complex. And what that means is that still we are not completely and fully understanding how boiling works, and that means for sure that we don't have a model that is satisfactory to model the boiling process. And that not only for the boiling heat transfer, but also for the critical heat flux, which is even more important, because critical heat flux is that point at which, from being very efficient, boiling starts to become dangerous, because it's the point at which the amount of vapor generated at the surface is so much that the heat transfer happens mostly to vapor and not to water. Vapor has a much lower thermal conductivity. The heat transfer deteriorates a lot, and there are all the risks involved with the damaging of the heating surface, which in a nuclear reactor is a quite critical safety. So it becomes a quite critical safety parameter. So the main idea was of the project was trying to develop more advanced computational modeling for the boiling process, moving from empiricism that still characterize the modeling of this process to more mechanistic principle, and try to apply those principles towards to being able to predict the critical heat flux. And the first step was look at boiling bubbly flows, which are only a part of the boiling process, because when bubbles are generated, then it becomes a bubbly flow. And the first question was, can we model bubbly flows? And the answer was, well, we can do better. We can do better in that. And because they are, even without considering the exchange of heat, even only considering a bubbly flows, an adiabatic bubbly flows without heat transfer, that's really a critical and quite complex flow. They are not important only in boiling, they are important in many engineering sectors. In chemical engineering, we find a lot of application in bubble columns, such as this example here. And they have many complex sub-processes inside, so the transfer processes of mass, momentum, and energy that can happen at the interface, the turbulence that in a multi-phase flows becomes different and with its own characteristic with respect to the single phase, and also the fact that in a bubbly flow normal there are hundreds, thousands of bubbles with different shape, different size, and those shape and size change with time and space. And so for this reason, the first step was to develop a CFD model that is accurate and robust as well to predict bubbly flows. And that model is based on multi-fluid Eulerian technique. I will describe that in the next slide. And we wanted it to be not only accurate but robust, so that can be applied with confidence to a very wide range of flow conditions. That is really important, more than, let's say, having a very good accuracy on some specific flow condition. Okay, so the model, as said, is multi-fluid Eulerian. So it's different with respect, for example, to interface resolving technique. So what happens is this. So considering a bubbly flow, and let's imagine that this is our computational grid. So we are solving in each one of these elements our system of equation. What we do is we average over every one of those elements. So what happens there is the single bubbles disappear, and what we end up with is an amount of gas identified by this quantity here, which is the volume fraction of the gas, and an amount of liquid. So the gas and the liquid will have their own velocity. They have their own system of equation that describe the flow. And the only thing we know is the amount of gas and liquid that there is in that specific space. And of course, the sum of the two is equal to 1. That is called, it's referred to a system that becomes of interpenetrating continua, which means if you look at here, now in each point you are in the liquid phase or in the gas phase. Once you have averaged those, you have gas and liquid in each point, and the relative amount is quantified by the volume fraction. Now that ends up in a model that is quite generally applicable, is not really computationally expensive, so can be applied quite easily to even complex flow condition with a very high amount of bubbles, and also with a quite, let's say, reasonable computational power. But at the same time, the problem is, by doing this, we lose the coupling, we lose the interface, so we lose the coupling between the two phases. So if we don't account for their interaction, so we have two velocities, and they are actually free to evolve independently of each other. And so there is the need to model the entire interaction between the two phases at the interface, which if you resolve with the required computational power, all the details is already accounted for. We need to account it for by adding additional terms, which are closure relation that try to account for the interaction between the two phases that we have lost in the averaging because we don't know now the details of the interface. And so that's our basic model setup. So we don't need the energy equation because it's an adiabatic flow now, a bubbly flow model. So we have only mass and momentum balance equation. And this is the set of closure we use to model the interface transfer. So we have a drag model to account for the resistance of the flow of one phase by the presence of the other. The lift force is the force that generates because we have a gradient in velocities, and so is a force perpendicular to the main flow of the bubbles. And other forces are wall force and turbulent dispersion force. So all of these takes into account the momentum interaction between the two phases. The model is implemented in the star CCM plus CFD code, but also we are trying to move, and we are in the process of moving the same modeling approach to OpenFOAM. And we have done a very extensive validation against experiment. We have compared against more than 30 cases of air-water bubbly flows, and you can see some example here. So this is a three-dimensional view of the volume fraction in a pipe. These are some velocity profile on a radial profile like this at some distance from the inlet. So in this case, 0 means that we are in the center of the pipe, and 1 means that we are at the wall. And what bubble does, this is the typical behavior bubble have enclosed. This is a quarter section of a pipe, so the flow enter from here and exit from the top. What they normally do, that's the general behavior, is as long as they are relatively small and spherical, they are pushed by the lift force towards the pipe wall. And you see that this is a void fraction profile, this one that is shown here as a peak at the wall. And it's important to mention for a slide that is a few slides after this, the peak is obtained by introducing a wall force, which kind of is active only near the wall and pushes the bubble away when they are too close, and was essentially introduced to be able to predict this void distribution. This one here instead is when the bubble becomes bigger, they start to be deformed, and instead of moving towards the wall, they tend to move towards the center of the pipe. And this is more or less the momentum interfacial closure. Now, the other areas we need to take into account in the turbulence is the turbulence and the effect the bubble has on the turbulence. So I've used a picture generated actually here. So bubbles has a big effect on the single phase turbulence field because they tend to alter the single phase turbulence field, and also they move around, displace liquid, and also generate wakes, bind, that generate additional turbulence. And so quite complex phenomena also this. And so we need, when we model turbulence, we have a turbulence model as in the single phase flow, of course, but we need to specifically account for this additional effect induced by the presence of the bubbles. So what we do, first of all, we use a Reynolds stress model, so not a two-equation model. And that means we solve an equation for each turbulent stress. We are able to take into account the anisotropy of the flow, which in some condition might be important, and I show something about this in a few slides. This is an example of the three normal stresses. You see that this is along the flow direction, and those are the other two directions, and you see that they are different in the three directions. That is captured by the Reynolds stress model. And also we account specifically for a source of turbulence due to the presence of the bubble, what is called bubble-induced turbulence model. And the base is that we assume that the drag energy is converted into turbulence kinetic energy in the bubble wakes. Here, so you have, this is the source with the drag force and the relative velocity, and this is the source of turbulent dissipation rate. And this is the time scales that I use, that from meeting this morning, I now know that I need to change. So already after half a day. And this is the last progress made. So instead of using, we still a Reynolds stress model, but now it uses the so-called elliptic blending approach. So is able to resolve also the region near the wall, allows a very fine resolution of the velocity and the turbulence field near the wall. And that's quite important because is a thing that is most of the time not taken into account in the model that are used. So this is the radial turbulent stress across the radius of the pipe. You see that it has a gradient. And because of that gradient, you have also a radial pressure profile in your pipe or in your channel. That means that in single phase flow, that is not particularly important if you are in a channel or in a pipe. But in this case, you have bubbles, and bubbles tends to move to this region here where you have the minimum in pressure. And for that reason, I really think that is an effect. It's not the only effect that moves bubble radially to obtain this profile, but that is a thing that needs to be taken into account to have models that are as general as possible. And in fact, I mentioned the wall force before because that wall force was introduced to obtain this profile, but it's a bit uncertain. There are people questioning the validity of, or the existence of that wall force. And when we use a model that resolves the wall region, we are able to resolve all this pressure profile as well. And these profiles were obtained without any wall force. And if we are able to do that, we can take away all the uncertainty related to the use of that wall force. So in my opinion, it's a more general model, and we should try to move to model that are Reynolds stress model and also resolve the near wall region for future, let's say, future development. And I think this is the last slide on this area, and then I will move to talk about polydispersity. That model has been benchmarked with the same model developed at AZDR, and I want to specifically mention this benchmark because there is an idea behind, and is what they called, and they started, is their baseline approach. So I've talked a lot about all these models. Also, you've seen all these closures, and drag, lift, wall force, exists, does not exist, turbulence model. In any of those models, there is some uncertainty. And that means that if we try to optimize on single experiment, we might end up with a model that is perfect for that experiment and doesn't work anymore when we change the flow. So what we were trying to do is select some closures, keep them fixed, and do not change them unless we see improvement over a very wide range of flow condition. And that was the idea of that benchmark. Applied our model without any change. And in the end, we saw that they were quite robust, they were quite accurate. We select a series of flow conditions, but between the two groups, we have really compared against a wide number of flows, and they provide a quite good accuracy, in particular on the void distribution. It's not perfect, but the errors are not large, and they can predict those flows quite well. And the area we identified here is as we probably already knew from the beginning, the bubble-induced turbulence area is the one that needs the major improvement. And we are already working on it. But I want to stress the importance of studies such as this, because we really have, if you go through the literature, we really have an immense amount of different models that are only slightly different because coefficients were changed only against a set of experiments or others, and that causes uncertainties in the future development of this kind of CFD models. Now, I would like to move to the other area, because we have talked about the interfacial closures and the turbulence, but we have not said anything about the bubble itself. No. Now, what happens is we don't have bubbles that are all the same type. When we have a lot of bubbles in a flow, they are all different. They have different shape, they have different size. And depending on shape and size, we have a different amount of interfacial area. And that's a key parameter, because you can imagine all the transfer between the phases. There can be mass, there can be energy, there can be momentum, happens on that interface. So the amount of that interface is critical to be able to predict these transfers. And so we have lost the knowledge of the bubble shape because of the averaging, and we need another way to be able to quantify the interfacial area. In particular, if bubbles are a lot different in the flow, and they can change their shape and size for multiple mechanisms. They can coalesce because of the turbulent motion. They can collide and coalesce in a larger bubble. Because of the same turbulent stresses on their surface, they can break up into smaller bubbles. This is still coalescence, but due to wake entrainment, so the bubble traveling beyond the first one tends to go faster because it's traveling in the wake and can coalesce with the first bubble, again generating a larger bubble. And for this reason we can have, as in this case, a distribution. This is the bubble diameter distribution in the flow that is quite wide. You see there is a peak of bubble around 3-4 millimeter and another peak of bubble of larger, 5 probably. And we need to be able to account for the effect of this, of the fact that the bubbles are not all of the same size. And what we do is we add what is called a population balance model. So it's essentially a model that, through additional transport equation, follows the evolution of the bubble population in the flow. Now, there are different types. The most simple only have here the transport of the bubble number density, so the amount of bubble per unit space. In this case, the model that we have tracks the bubble distribution, or the moments of the bubble distribution here. I don't want to go very much into the details, but what happens is that when you know moments of this distribution, you can derive average bubble diameter. So you can characterize your distribution with an average value of the bubble diameter. The most used is the so-called Sauter mean, which is obtained from the average volume of the bubble and the average surface area. And you see they are obtained resolving this transport equation. You see here the source term for breakup that accounts for breakup and coalescence, and also if there is mass transfer, you can have a source due to mass transfer. So let me show some result of again, also this population balance was validated against a number of cases. You see an example here. In this case we had, and that's very important for this area, we have measurement of different axial distances across the pipe. So what we were able to do is fix, you see here that the CFD results matches the experiment perfectly. The experiments are the symbol, but that's because we imposed that distribution at the inlet, and we were able to follow the evolution of the bubble diameter. This is the second measuring station, this is the third. You see that in the center of the pipe is not bad, at the wall a bit less good, probably because we have too much breakup in our model in that area. And I want to describe this experiment a bit more because what we did was, I mentioned before that small bubbles tends to stay in the wall region and larger bubble tends to move towards the center. So what we did here, to be able to predict also very complex condition where you have a mix of these two, we have two different populations, one of spherical, let's say, and one of deformed bubbles. And you see the evolution of the volume fraction of each along the pipe in these two cases. So at the beginning, you have a lot of small bubbles that stays in the wall regions. As long as the flow develops, the amount of those is less and less because they tend to coalesce and form larger bubbles. You see that here is almost zero, but it increases because larger bubbles are formed, and these larger bubbles move toward the center of the pipe. And by doing that, we are able to predict this bubble distribution, this void fraction profile, that has a peak at the wall and also a peak at the center. And also we can look at the results for the bubble diameter distribution. Moving from two peaks, we develop a distribution that have a wide range of diameters, but a single peak because larger bubbles are formed in the center. And we applied those models not only to pipe flows. I've only talked about pipe flows, but we have some simulation also of bubble columns. And in this case, bubbles are injected from the bottom in a stagnant liquid, as in this case. and we are able to predict the evolution of the bubble inside the liquid, and the velocities, and also the volume fraction inside the liquid. And so after having gone through all these physical aspects, we were finally able to move to the boiling flows, which was supposed to be the starting point. And I introduced in the model also the boiling aspect. So the boiling is modeled using what is called the heat flux partitioning approach. So if we boil, we have bubble generated at the wall. What means is that some heat is transferred to the fluid as if it was alone. Some heat is transferred to the bubble. And some heat is transferred because when the bubble departs from the wall, it generates additional movement that generate additional heat transfer. And essentially what the model does, it calculates the three components separately, and in that way account for the boiling, additional boiling component at the wall, and from the heat flux determines a wall temperature. Those are single phase convection and quenching. I want to focus on the evaporative heat flux. So the evaporative heat flux is calculated from what is called active nucleation site, so the number of nucleation sites where bubbles are generated at the wall, the departure diameter of the bubble, so which diameter they have when they depart from the wall, and the frequency of departure. So it's essentially a mass flux of a volume flux of bubbles from the wall with the enthalpy. So it's an energy flux that is taken away because of this bubble. The problem is that, as before, we had a lot of parameters that we have to determine. And as before, to do that, we need closure models. Because we don't know. We have averaged everything, so we don't exactly know the bubble. And those are essentially every time calculated with empirical correlation. I've mentioned some in the slide. Those are some examples. And what you have is this is a results, again, evolution of the volume fraction of vapor. You see at the beginning is 0, so there will only be liquid, and then the liquid will heat up, and here it will start to boil, and you will see the volume fraction be quite high at the wall because of the generation of bubbles. Now the problem is that when I try to test this correlation against a large number of flows, not only the results were not good, there's not a single combination that you can use and will give you not accurate results, but results on all those cases, because they are quite sensitive to the condition. So most of the time, not most of the time, but you find some combination that works well with some condition, but does not converge in other, and the opposite for other combination, which tells that we need to move away from those correlations, and we have to try to include more physics, because they are essentially based on macroscopic parameters that do not capture really the physics of the boiling process at the wall. So this is instead the model I developed to try to include more physics into that kind of model. It is based on a force balance. So essentially, when there is, it starts from the balance of the forces that act on the bubble when it grows at the wall, and it takes into account surface tension that tends to keep the bubble attached, the drag effect from the flow that will take the bubble away, the buoyancy, because the bubble is lighter, will tend to rise. So from this balance, until they are 0 or negative, the bubble stays attached to the wall. But when they turn positive, it means that the bubble departs from the wall. And so from this balance, the bubble departure diameter is determined is hopefully a more physically based way. And when the bubble grows, the growing of the bubble is calculated with this heat balance. Essentially, heat is coming from the surface of the bubble and will cause evaporation and the growth of the bubble. So we account for superheated liquid that transfer energy across the surface. On the top, the eventual presence of subcooled liquid, so that will take some heat away from the bubble. And also we account for, the model accounts for the micro layer, which is a thin liquid layer that is trapped beneath the bubble when the bubble is growing. And that is essentially, in a few words, the basis of the more mechanistic, let's call it in this way, model for boiling. That has been tested, again, databases of saturated and subcooled boiling, and I want to talk a bit more about this case, which is quite complex, because in this case there is there are some horizontal, is an horizontal rod bundle with a cross flow, and measurements were taken on a single tube here, and different configurations were analyzed. So with the heat only on that tube, with the heat on different tube as well. And in all those conditions, even though it's quite difficult to predict because you have temperature fields that are different in all the different setup, and that affect, of course, the evaporation and the growth of bubbles on that specific rod, but still the model was in quite good agreement with the experimental data, keeping in mind that in this area, good agreement means 30–50%. That's probably, if it's below 30%, is probably quite good agreement can be said. And in the plot, you see this is the departure diameter as a function of the wall temperature. And here instead is for two cases, the departure diameter calculated by the model and the one in the experiment. So you see that most of the data are inside those error bound, which I think are ±30 here and ±50 in the other case. But again, there is a lot of uncertainty involved because also in the measurement of this process. And then the last part was, I forgot to mention that this model was developed outside the CFD code. It's a MATLAB model that runs standalone. And the last part was implementing this mechanistic model inside the CFD, which has been done. And you see an example here is the same void fraction profile for another case, but is up and running. It works, produces well, good results. As you see here, this is the wall temperature along a pipe, and the model has also been compared against other available. And it's used not only to evaluate the bubble departure, but also to evaluate the other parameter, which was the frequency, because since we know the growth of the bubble and the time the bubble takes to grow, we can also calculate the frequency of departure from the heated surface. And other than that, at the university, we are trying to develop also different techniques. For example, we have a PhD student working on instead interface resolving method. So in this case, the bubble is fully resolved. But I don't have to spend a lot of time talking about this method, probably because there is much more expertise here. But so we have cases of bubbles in a turbulent flow, as in this case, and of a single bubble in a turbulent flow, and also of multiple bubbles. So, but the main idea here is those for the other model, the one that the multi-fluid model, the closures are really important. And there is a lot of uncertainties in those closures, because similarly as for boiling, they were developed from experiments. Some are really old. And what these simulations are capable of doing is making available knowledge that is difficult to gain even in the most advanced experiment. They really are able to provide details of the flow that are fundamental to develop better closure for the more macroscopic model. And but this is an activity only started with this PhD student, and hopefully we'll develop more in the next few years. And instead, I want to spend a few minutes talking about this, which is the most recent activity I've been involved. I'm spending time on, let's say. So I've talked about bubbly flows, but of course, when boiling occurs or in other situation, actually it's difficult to find a real situation when you have only a bubbly flow. Most of the time you have a transition between different flow regimes. So you can have bubbles, you can have larger slug. In a boiling channel, you start with bubble, then you develop a slug flow, then you develop an annular flow with a film of liquid and droplet of liquid inside the gas. So you go through all these different flow regimes. And in any of those, the closure required by the multi-fluid model will be different. And that's a big challenge, because also the multi-fluid model it doesn't work really. It works well here. It doesn't work really well when you have very large segregated interfaces. And a model that works really well here in the interface resolving model. Of course, the interface resolving model works well also here, but you need a lot of computational power to be able to resolve all the details of all the bubble. So the idea here is to try to include some kind of interface resolution-like capabilities inside the multi-fluid model, so that we are able to follow the evolution of the flow in the different flow regime, and possibly being able to predict flows as complex as this. This is a experiment on a loss of coolant accident, where you have large interfaces and a lot of small droplets or bubble. So essentially what we're trying to do is use a multi-fluid model to start with, and when a large interface such as this is detected in the flow, the interface resolution is activated, and we have a compression that is activated to keep the interface shape. Because the main drawback of the multi-fluid model is that it tends to disperse a lot, these interfaces. So we have tested that for the very fundamental cases, but you see here a simple rising bubble rising in water. And this is how the model works. So you see that red area there. That is the area where this large interface is detected. The compression is activated only there in that area, and the model is able to maintain the interface sharp. Keep in mind that we still have two equations. We have two velocities, not one, as it happens in the interface resolving model. And other than the interface compression, what the model does is activate surface tension in that region, and also change the drag model from a bubble-based model on a model that is more proper for this kind of interfaces. And you see the results here. The black line is the generalized model, and the other are some DNS simulation of using volume of fluid. And the results are in quite good agreement. At the same time, the model is still able to predict a pipe flow where the flow stays dispersed, the compression does not activate, and we have the same void distribution that we have seen in the previous cases. Okay. I'm good on time. So this is more or less the research on this area of multi-phase bubbly flows and boiling and the recent development. Now I want to spend the last part of the presentation to talk about another application that we did and was, as I mentioned at the beginning, the use of CFD to evaluate passive cooling. Okay, there is a lot of attention now on the introduction of passive cooling system in reactors. Some have already operated. So, so we think that we also need computational models that are able to predict passive cooling and natural circulation flows with accuracy, so that provide us with a tool that is able to evaluate passive cooling effectiveness with confidence. And the passive cooling system we have focused on is the external reactor vessel cooling, which in case of an accident that involves the melting of the core is kept inside the reactor vessel and the vessel is cooled by natural circulation on the outside, and we expect boiling to happen there, which means our limit becomes the critical heat flux. It's very complex because we have all the complexities of natural convection plus the boiling. And so we wanted to test the capability of the CFD to predict this flow and the boiling condition and the natural circulation as well. And this is the geometry we modeled, because this was an experiment done by collaborators in India. Is the vessel of the pressurized EV water reactor, and they use melted glass inside the vessel, and the vessel was in a pool of water, and they allowed the vessel to cool for some hours. And the good thing is that they have measurement for many hours. And you see here the data available. This is the heat flux on different locations across the vessel wall. And we use that as a boundary condition in our CFD model. And you see the results here. There is some boiling at the beginning, and then the temperature drops down as the transient goes on. You see it's 2 hours of transient predicted by the model. You see that here the temperatures are really low, because the problem was that we started from Reynolds average and Navier-Stokes, so K epsilon, K omega, the usual turbulence model. And what happened is the model predicted complete mixing in the pool. And if there is complete mixing, it means that the average temperature, more or less, the pool is all at the around the average temperature. Instead, what they observed in experiment was a strong thermal stratification. And since the temperature of the water is lower here in the simulation, also the wall temperature becomes lower. So I moved to a different turbulence model, and I tried to use large eddy simulation to predict that flow by using in OpenFOAM. This was done in OpenFOAM. And you see here the vessel temperature predicted by the large eddy simulation are much more in the area of the experiment. And this is instead the thermal stratification in the pool. The symbols are measurements taken at different height from the bottom of the pool to the top. And you see that basically the bottom of the pool doesn't do anything. So it just stays more or less at the initial temperature. Instead, the top heat up, and using large eddy simulation, the model was able to predict this process. But this was only done in single phase, so there was no boiling model and no two-phase model in this simulation. And well, there are some nice video that can be shown for this case. This is the velocity. You see the buoyant flow at the top of the vessel, because the water is up here and recirculated there. and the temperature field developing and eating up and up and up on the upper part, but stays more or less at the same temperature at the bottom. So the last slide, which is not really a conclusion, is more a future development, let's say. So I've tried to talk a bit about the different model, and the idea is to continue in this development. Let's say keeping this multi-scale approach. So multi-fluid model to predict large macro scale, industrial scale, let's say, multi-phase flows, and a continuous improvement of the closure to make the model robust, and a validation of this model with databases as wide as possible. But at the same time, the coupling and the use of interface resolving technique to understand better the smallest details, the smallest physics of these flows, and generate understanding that can be used to improve the macroscopic closure. But at the same time, apply these models to much more complex conditions with the continuous development of computational resources. And at the same time, try to put these together in what I call the generalized multi-fluid model to reach applicability across the different flow regime, and ideally being able to selectively resolve specific region of the flow where we think that resolving all the details is more important than in other regions. And for the other two, continues in the mechanistic development of the boiling model, and being able to apply that model to natural convection or passive cooling, and include also high fidelity, let's say, capabilities such as the LES that might be required to predict some specific phenomena such as the thermal stratification and the natural circulation pattern in that water pool that I've shown. So that was the last slide. So thank you very much for your kind attention. I'm happy to answer any question now.
So this is not my field, but when you're talking about the little bubbles migrating to the side, in my head, the way I understood that is that they effectively have a higher viscosity, and so they just migrate to where the flow is lower. The little bubbles to go to the side.
They do that because, let's see if I have a. No, I don't have that. Well, because essentially there is a shear flow, so the velocity is lower at the wall, right? But the bubble moves more or less at the same velocity. So the velocity of the fluid around the bubble becomes different on the two sides, and so tends also to push the bubble in. The pressure distribution becomes different on the two sides of the bubble, and tends to push the bubble towards the wall. Because the
lift force, right?
Yeah, yes. Is a lift, yeah. Because the relative velocity between the fluid and the bubble is higher on one side than in the other.
So I really liked your generalized multi-phase model. It's kind of like the interfacial equivalent of LES almost. But I was wondering, is it kind of a step closer to a two-fluid four-field model, or how is it different?
It's not really a four field because it keeps the same two field. Then being able to handle the entire transition from bubble dispersed in a liquid to droplet dispersed in a gas will be quite tough. But the difference is that one of the differences is that in this case the switching is not activated based on general flow regime maps. It's activated locally based on the gradient, for example, of the void fraction, or can be activated also based on the population balance result. So in that way, I believe it's different with what there is available. But again, it's similar in the sense that still we have to use closure for the two regimes. So also for the segregated, but the dispersed. So the dispersed and also the segregated. So it's not really an interface resolving. It tries to have a sharp interface, let's say. That's the main. Well, yeah, probably the force field doesn't do that. They don't keep the interface sharp and.
If you could go back into the slide where you had a graph of alpha versus the diameter of the bubble.
Yes.
You had two peaks.
Yes.
Yeah. So the diameter of the bubble is basically in this region with these two peaks. No other bubbles with any other diameters. Is that the experimental value or that?
That's the experimental values. No, the bubbles are in all these between 3 and 6 millimeter. That flows as bubble between 3 and 6. Those peaks means that the majority of bubbles are of this size and of this size.
And what distribution do you put? Do you assume for such an experimental distribution? So what are the equivalent distribution that you use within the model itself?
Okay, in the model we use a population balance with two different groups of bubbles that interact with each other. So we start here with all, let's say, all bubbles of this size, of the left peak, and when they coalesce, when they start to become bigger than a certain size, they transfer to the second group, and the second group instead moves to the center as different values of the closures. And that's that's why because you can't do that with a single value of the average bubble diameter. So there are other methods. For example, you can divide these in a lot of classes, but still you have to account for the different behavior of the two groups to be able to predict that.
Does the surface condition affect bubble departure diameter?
Yes.
And does your model account for it?
No, not really. No. The surface, you mean the surface characteristics? They are kind of included in this active nucleation side parameter. That's probably the most uncertain things that there is in boiling. I believe it's really difficult to properly account for the specific characteristic of the surface.
Can the user specify somehow the properties of this surface using this model?
Yes, in the sense that, but you still have to specify the active nucleation site, so the number of nucleation sites active on that surface. Then you can specify whatever values you want. So in that way, yes. But if you mean specifying the details of the surface and their effect, not at this point. Because also it goes to a scale that is really small, and the effect on the surface. So there are correlations that tries to account for that, but they are, because then it depends also material specific, and it's quite tough to be accurate on that.
So when we try to model visual oriented distribution errors, like say like a drag vortex or a T-force, so how can you make sure that the correct physics is modeled by the closure?
So if I understood, so you mean how I'm sure that this model really represents the physics of what I'm trying to predict. That was the question, right?
Yeah, I mean, I've seen like this paradigm like for multiple literatures before.
Well, they are closures that have been developed based on experiment on bubbly flows. So they are more or less accurate on bubbly flows. Of course, when your flow changes, these closures need also to change, and that is the tough part, to apply this model as it is to a flows that change regimes. I mean, there has been a lot of work done on bubbly flows for this closure. So until we stay on the bubbly flow, they quite behave in a reasonably good way. Outside, much less.
As long as we consider 50%.
Well, yeah. Well, that's multi-phase flow, so we are allowed to do that. But yeah, and of course, by testing them quite extensively over different flow conditions.
Right, let's thank the speaker once again.
Thank you very much.